recognize that science is not static. The clash between Einstein and quantum mechanics exemplifies the dynamic nature of discovery, where each answer leads to new questions, each experiment opens new possibilities, and each insight challenges our assumptions. Reality is not a fixed monolith, it is a living, evolving tapestry shaped by underlying principles and phenomena that we are only beginning to comprehend. By embracing this perspective, we cultivate intellectual humility and resilience, acknowledging that the pursuit of understanding is a lifelong journey, and that the universe is far more intricate and beautiful than any single theory can fully capture. The interplay of deterministic and probabilistic frameworks invites us to explore the unknown with curiosity, wonder, and courage, recognizing that mystery is not a limitation but a source of inspiration. When we contemplate the profound divergence between Einstein's relativity and quantum mechanics, we must first appreciate the revolutionary impact of each framework on how humanity perceives reality. Einstein's theories of special and general relativity reshaped the very notion of space and time. No longer fixed backdrops in which events unfold, space-time became a dynamic fabric capable of warping, bending, and stretching under the influence of mass and energy. This insight was not merely academic, it had profound implications for our understanding of the universe. Black holes were predicted as regions of space-time where gravity becomes so intense that not even light can escape. Gravitational waves were theorized as ripples traveling through the fabric of the cosmos. Time itself became relative, varying depending on speed and gravitational influence. These ideas challenge our intuitive understanding of reality, forcing us to recognize that the universe operates according to principles far stranger than the everyday world we experience with our senses. In stark contrast, quantum mechanics exposes an entirely different domain of strangeness, operating at scales far smaller than anything we can directly observe. In the quantum realm, particles behave in ways that defy classical logic, existing simultaneously in multiple states, being entangled across vast distances, and responding to the act of measurement in ways that seem almost supernatural. The famous thought experiment known as Schrödinger's cat captures the paradox perfectly. A cat placed in a sealed box with a quantum-triggered poison exists in a state that is both alive and dead until observed. This is not merely a philosophical puzzle, but a reflection of the probabilistic nature of quantum reality. The very act of observation collapses the probability wave into a definitive outcome, suggesting a universe in which observation plays a central role in determining reality. The implications of this idea extend beyond physics into philosophy, metaphysics, and even consciousness studies. One of the most mind-bending consequences of the quantum framework is entanglement. When two particles become entangled, their properties are linked such that the measurement of one instantly determines the state of the other, regardless of the distance separating them. Einstein famously referred to this phenomenon as spooky action at a distance because it appeared to violate the principle of locality. Subsequent experiments have confirmed that entanglement is real and that particles can remain correlated over distances exceeding hundreds of kilometers. This challenges the classical notion of independent objects existing in isolation and suggests a universe in which interconnectedness is fundamental. The philosophical ramifications are enormous. If reality at its core is entangled, then separateness may be illusory, and our actions may resonate through the cosmos in ways we are only beginning to grasp. Bridging the gap between Einsteinian relativity and quantum mechanics is one of the greatest challenges in modern physics. The pursuit of a theory of everything represents an ambitious effort to reconcile the deterministic macroscopic world with the probabilistic microscopic realm. String theory proposes that the fundamental constituents of reality are not point-like particles but one-dimensional, vibrating strings. Each vibrational mode corresponds to a different particle and force, and these strings exist in multiple dimensions beyond our familiar 3 dimensions of space and 1 of time. Loop quantum gravity offers an alternative vision in which space itself is quantized, forming a discrete granular structure rather than a smooth continuum. Both theories aim to unify gravity with quantum mechanics, providing a coherent understanding of the universe from the smallest to the largest scales. Though neither theory is complete or experimentally confirmed, they illustrate the profound creativity and rigor scientists employ to understand the ultimate nature of reality. Consider the practical implications if unification is achieved. The ability to reconcile gravity with quantum mechanics could revolutionize technology, allowing for precision control over energy, matter, and information in ways previously unimaginable. Quantum computers already exploit principles of superposition and entanglement to perform calculations at speeds far beyond classical machines. Advances in understanding entanglement and space-time could lead to communication systems that are instantaneous and secure, and energy systems that tap directly into the fundamental fabric of reality. Space travel could be transformed by technologies that manipulate space-time geometry, allowing for faster-than-light travel within the framework of relativity. Medicine could benefit from quantum simulations that model molecular interactions at unprecedented precision, accelerating drug development and personalized treatments. The unification of these theories promises a future where our capacity to interact with the universe is limited only by imagination. The philosophical and existential implications are equally profound. In a deterministic relativistic universe, every event is the result of prior conditions leading to a predictable chain of causality. In contrast, the quantum domain introduces indeterminacy, allowing for multiple possible outcomes where probability governs rather than certainty. This raises profound questions about free will, agency, and the nature of choice. Are our decisions predetermined by prior states of the universe, or are they influenced by probabilistic events at the quantum level? This duality invites a re-evaluation of human responsibility, creativity, and morality, suggesting a universe that is not simply a mechanical clockwork, but a dynamic, evolving field shaped by both necessity and possibility. Embracing this duality nurtures humility, curiosity, and a profound sense of wonder, encouraging us to explore the unknown, while accepting uncertainty as an essential aspect of reality. As we explore these concepts further, we encounter the notion of time, not as a linear progression, but as a malleable dimension, subject to warping and relativity. Time dilation occurs when objects move at velocities approaching the speed of light or exist in strong gravitational fields, causing clocks to tick at different rates relative to each other. This is not theoretical speculation, but has been confirmed experimentally with precise atomic clocks on airplanes and satellites. The effects are subtle but measurable, reminding us that the universe does not operate according to everyday intuition. Quantum theory adds another layer to this complexity, suggesting that events at the smallest scales do not follow a fixed temporal order, but exist in a superposition of possibilities until observed. Combining these insights produces a vision of reality that is simultaneously structured and fluid, probabilistic and deterministic, interwoven with mystery and law. Human consciousness and perception play a critical role in navigating and understanding these complex realities. The quantum observer effect implies that measurement influences outcomes, suggesting that awareness itself is an active component in the unfolding of events. Neuroscientific studies indicate that our perception of time, space, and causality is shaped by cognitive processes that are themselves embedded in a quantum and relativistic framework. This raises fascinating questions about the relationship between mind and matter, suggesting that consciousness may not simply be a passive witness to reality, but an integral part of its formation. Practices such as meditation, visualization, and focused intention may allow individuals to engage more consciously with these underlying structures, creating subtle shifts in experience and perception. Einstein's discomfort with the indeterminacy of quantum mechanics highlights the philosophical tension between elegance and uncertainty. He famously stated that God does not play dice, expressing his unease with a universe governed by probability rather than strict causality. Yet experimental evidence consistently supports quantum predictions, suggesting that randomness and probability are fundamental aspects of nature. This tension invites reflection on the limits of human intuition and the necessity of empirical investigation. It also underscores the importance of embracing complexity and ambiguity as essential features of reality rather than obstacles to understanding. By integrating both relativistic and quantum perspectives, we gain a richer, more nuanced appreciation of the cosmos as simultaneously comprehensible and infinitely mysterious. Exploring the practical applications of these insights leads to exciting frontiers. Quantum sensors capable of detecting minute fluctuations in gravitational fields or magnetic energy can map the universe with unprecedented precision. Quantum communication networks exploit entanglement for secure transmission of information impossible to intercept or tamper with. Quantum simulation allows researchers to model complex systems from molecular chemistry to climate dynamics, accelerating discovery and innovation. Relativistic principles enable the development of technologies that account for time dilation and gravitational effects, ensuring accuracy in navigation and communication across vast distances. The interplay between these domains of physics drives technological innovation and expands human capability in ways that would have been unimaginable just decades ago. Finally, the interplay between Einsteinian relativity and quantum mechanics invites us to reconsider our place in the cosmos. We are participants in a universe that is simultaneously deterministic and probabilistic, structured and flexible, interconnected and dynamic. Our understanding is provisional and constantly evolving, shaped by observation, experiment, and reflection. By embracing the paradoxes and mysteries of reality, we cultivate humility, curiosity, and resilience, preparing ourselves for discoveries that challenge our deepest assumptions and expand our capacity for wonder. The clash between Einstein and the quantum pioneers is not simply a story of scientific debate, it is a profound exploration of the universe itself, revealing layers of complexity, beauty, and mystery that continue to inspire exploration and reflection.